Yeah, good morning everybody. Welcome back. Start with the routing protocol. We start with the routing protocol. Uh, I guess in the last class we have talked about various sorts of routing we have talked about various sorts of routing like distance vector routing and then link state routing, hierarchical routing. I think we talked about all these sorts of routing scheme. Uh, the the issue which stays is that how are these routing schemes practically implemented. So I will talk about a bit of IP scheme, which is used to implement the theoretical routing schemes. Okay, which is used to implement the theoretical routing schemes. Okay, this is the idea this class, and then we'll talk about a bit of peer-to-peer networks and talk about the CORD protocol. Okay, coming back to IP. So what we know now is that IP scheme is the default addressing scheme for routing. And what is a IP? Basically, IP is so what is an IP address? First of all, what is an IP address? We know typically an IP address can be 10.3.7.6 or 192.126.2.3. Okay, so something like this, which has 4 tuples. Okay, and each tuple can take up till from 0 to 255. Okay, so this is what type of addressing scheme? This is what we call IPv4 addressing scheme. Okay, so this is what we normally call is a IPv4 addressing scheme. Fine. So what is happening? That we have a 4 tuple and this 4 tuple, each tuple can be of from 0 to 2 to the power 255. That means 0 to 255 means 2 to the power 8. So 2 to the power 8, 2 to the power 8, 2 to the power 8. That means this IP can have 2 to the power 32 addresses. Okay. So now what is, first of all, I think I talked in the previous class also, but let me again reiterate this. How much is 2 to the power 32? Roughly 10 to the power 10 or 32 into 0.3 is 10 to the power 10. Let us say it's roughly 10 to the power 10. So 10 to the power 10 means what? That how much is 10 to the power 10? It is so 10 cube is 1000, 10 to the power 6 is million, 10 to the power 9 is billion, so it is 10 billion. Okay, so it is 10 billion addresses which are available. And roughly how many people are there in this world? Around 7 billion. So it is roughly 1:1. Okay, address is possible. But what we know is increasingly each individual has 3-4 devices and each will have different IPs. Okay, each will have different IPs. So how can this 10 billion IPs be sufficient for all these purposes? And this 3-4 may go to 7-8. Your lock will have IP. Is the what is coming? Your lock will have IP. Okay, your fridge will have IP. So every device slowly may begin to have IPs. Okay, every device may slowly begin to have IPs. So now how will this IP addressing scheme actually encompass or actually accommodate all these sorts of device? So this is an open question which we will talk a little bit in the class. Okay, again coming back to the original part, that IP addresses, how will this IP addresses be understood? Okay, so this is a question which we can ask, that I have packet. Okay, I have a packet which is a data packet which I want to send. And how will I understand? From this packet? How will I understand from this packet that the packet? How will I means I say router. Okay, understand that the packet needs to be delivered to some destination X. Okay, and there are other questions also, that how will these packets be delivered? Means how means that whether how will these packets be delivered, that whether it will be delivered, say lazily. Lazily means whenever the traffic is less, say I'm just cooking up something, traffic is less, or on urgent basis, something like this. Okay, or on urgent basis. So this is something which we will see. So this is some of the questions which needs to be answered. And how will this data packet understand? From the header which each data packet has. And now we will talk about this header. Okay, header which each data packet has, and let us now talk a bit about this header. Okay. Okay. So now if I see the IP header or the IP header, so how is the IP header looking? So IP header has various fields. Okay, so various optional fields and compulsory field. Okay, so it has various optional field and compulsory field. So the first field which is important, if you think, these two will stay: source address and destination address. So these are the two things which will necessarily be there: the source address and the destination address. Okay, so source address means source IP, say 10.7.6.7, and destination IP, say 10.6.7.6. Okay, so you are trying to send from one source to destination. Now let us come to other fields one by one. So now the version. The first field is version, which is telling whether it is IPv4 or IPv6. Okay, and here default everything is IPv4. So again I have told previously also that although IPv6 has been proposed, but IPv6 is not used. Okay. So next is IHL. How long is the header? Okay. So what we see is, see there are, if you see here, if you see here, see there are 1, 2, 3, 4, 5. So there are 532 bits. Okay. So 532 bits or 5 lines which are compulsory. Okay, and then beyond that there can be 10 more lines which are, there are 10 more lines which are optional, 10 more lines which are optional. Okay, so that means how much? That means total is 15 lines, and 32 bit means 4 byte. So 15 into 4 is 60 bytes. Okay. So there can be 60 bytes at most which can be there. So now the third point is type of service. Can be like, you can think that what type of queuing, what type of services, what type of queuing options. So if there is say in a router, okay, if there is a queue, okay, and if there is a priority queue, okay. So what the priority queue, you know that there can be like 2-3 queues parallelly running, but some has more priority than other. Okay. Some has more priority than other, more priority than others. So now you can actually define the priority. So now you can actually define the priority through this, whether you need a high priority service or a low priority service, etc., etc. Okay, and then this field is a total length field. Total length field is the total length of the packet, the total length of the packet, and that is what? Header plus data together. Okay. So what is IHL? IHL is just data, while total length is header plus data together. Okay. Is this clear? Okay. So next is identification field. Okay. Identification field is, see, the explain you a bit about IP layer and TCP layer. So let's say a packet is coming from TCP layer. From the TCP layer, it comes to the IP layer. Okay. Or it can be UDP, it's a TCP layer I am telling. So it can be a UDP packet, okay, which is coming from the TCP layer to the IP layer. Fine. It comes to the IP layer, but this packet is big. And my router can only forward smaller packets, say. Then what will happen? Then I have to divide this packet. Okay. So although this is one packet at the TCP layer, but it gets divided in the IP layer. Okay. This can happen. And so this field, that identification field, is telling that all those packets which has the same identification number are actually part of the same packet. All those packets in IP layer which has same identification number, all those packets in IP layer which has same identification number in TCP layer, or it may be a UDP packet, that is why it is called datagram. Okay, it is a UDP packet, say in the TCP layer has all those which has same identification layer of the same packet in the TCP layer. Okay, please have this clear, that again I am telling a packet comes from TCP layers and it comes to the IP layers, but this packet is big and the router cannot forward big packets. Then what will you do? There are two things which can be done. One is that you identify fine. There are two things here. You say that I discard. So you can discard. So that is of no use. If you discard, that is of no use, because if you discard, that is of no use. So what you have to do? You divide the packets into smaller halves. So now if you have divided the packets into smaller fragments, in the header you have to identify that all these fragments actually belongs to the same packet, and that is done through this field identification. And now with that identification there are 2 points, that DF and FF. DF means don't fragment, meaning that meaning that this packet is not fragmented, this is one packet, and MF is more fragments. So if this is 1, that means this is one packet, it hasn't been divided like what I showed, and if MF is say 0, MF is 0 means this. So see, okay, just to be clear, that when you have MF and DF, so DF 0 means no, DF 0 means no fragmentation. Okay, is that clear? DF 0 means no fragmentation, while DF is equal to 1, while DF is equal to 1 means, while DF is equal to 1 means fragmentation. Okay, and MF means, MF is equal to 0 means this is the last packet of fragmentation, while MF is equal to 1 means more fragmented packets with the same datagram number is expected. Okay, fine. So, more datagram number is expected. I guess you are getting it. Okay, so the other thing is, say, time to live. Time to live is an important component. Time to live means for how many hops will the packet stay alive. What does that mean? That a packet goes from one router to next router to next router to next router to next router. So, if it continues to go on, after some time the packet will be dropped. Okay. So, typically if you think, say you want to go from one place to another place by aeroplane. So, if you want to go from one place to another place, place 1 to place 2 by aeroplane, how many hops will you take? Either 1 or 2 or at most 3. In very rare cases 4. Okay. So, not more than 4, there is no hops more than 4. Okay, it is not possible. Okay. Then if you are going by more than 4, basically you are joyriding. Okay. You are not going by the optimal path. So, this part is incorporated into this TTL, that after 4 writes finish. Okay. So, this is incorporated through the TTL concept. Okay. And then header protocol is, what type of protocol is this? Actually now in IP the entire protocol is IP protocol. So, there is no variation here, IP protocol. So, that is there. Then header checksum is a checksum which takes all the bits into consideration, all the header bits into consideration, and put some parity bits or some CRC bits, okay, CRC bits to check if to ensure that the header doesn't get corrupted. Okay, okay, and then you have the source address and the destination address. I guess this part is fine. Okay, so now the optional part. The optional part. So, optional part can have 5 fields. Okay. So, you can have like security first. What does security means? Security means that whether some encryption is maintained, etc., etc. Okay. The second is strict source routing. So, strict source routing means, so what is happening in routing? We have seen that the routing path can vary. So, one packet 1 going this way, packet 2 going this way, packet 3 going this way, according to the optimality at those points. Okay. Now, strict source routing tells no, this complete path should be followed. So it actually, see, this is interesting because what we know, IP is a connection-less protocol or a connection-oriented protocol, or connection-oriented protocol. So what we know categorically, IP is a connection-less protocol. What does connection-less protocol means? That we are not worried too much about the path. The path can be anything, but this is in complete violation of connection-less protocol. So this, adding this makes IP a connection-oriented protocol. Okay. But this is an interesting thing is that the header has that flexibility, or the protocol has this flexibility, that although in principle it is a connection-less protocol, but for special circumstances it can actually accommodate a connection-oriented architecture. Okay. The next is loose source routing. Okay. So what is loose source routing? Loose source routing is you don't give the entire path, but say you are going from USA to India. Okay. So you can go this way or you can go this way. Okay. And your intention is you want to actually ensure that the packet goes this way. Okay. And you don't mind whether it goes like this or like this or like this. So you are not so nitpicking about the way it goes, but you want it to go from left to right or right to left. You always want it to go from right to left. And how can you ensure? You can ensure by specifying one or two routers in between. You can specify that no, it should go to from USA to Germany, to Uzbekistan, okay, Uzbekistan to India. So in between it can go anyway, in between this can go anyway, but as soon as you have mentioned Germany and Uzbekistan, then it has to go with all probability from right to left. It cannot go the other way around. It cannot go the other way around. So that is what is called strict source routing. That is what is called strict source routing. I guess this is clear. Fine. So next part is next part is what? Next part is record route. So this may be used for debugging, okay, or some may have higher security concern that all the routes, all the router through which the IP passes, the packet passes, you put in the IP of those routers inside the packet. Good. And timestamp is even better, that not only you put the router's address, but also the time when the address was accessed. So this is how the IP header works. Okay. So there can be various algorithms which can be used there can be various algorithms which can be used in the security protocol. There can be various algorithms which can be used in the security protocols, like SHA1, okay, SHA1, SHA2, okay, or you can have the encryption protocol like DES, okay, AES. Something of these protocols are used for the security purpose. Okay. So SHA-1, SHA-2 are hash functions, okay, which are used, okay, secured hash functions, or the DES things are used. Fine. So now I guess the header part is clear. The header part should be clear. So now let me talk a bit about the IP address again. Okay. So IP address, as you understand, first of all, it is not, there were historical reasons why it was put into like 7.7.6.7. Okay. So why there are these 4 dots is more due to historical reasons. I think in present part there is not much, there are some rules, but this is more due to historical reasons. Why, I'll tell you. See, there are, first thing was the classful addresses. Okay. First thing was the classful addresses, and what we said that there are class A, so which is like which will have a 0 in the front, and everything is, there is a network and there is a host. Okay. So half of the network was class A. Okay. And class A, they thought that this will be used for very big servers. Okay. Big servers. Okay. So that was the idea of class. Then class B was 10, class B was also 10. 10 means one fourth of all the IPs, and here also it was thought that this would also do medium range servers. Okay. And then for all home purpose or home or small purpose, it was 110, that means 1/8 of all the IPs. Okay. All the IPs was class C. And if you think 110, what does 110 means? You see, starts with 192. And those who of you are a bit senior will know that initially all IPs used to start from 190. Okay. So 192.168.7.6. So something like this was the initial IP, because the initial concept was classful address, and that's why people did this 4 class classifier, because there was also subnet concept, but this 4 class was initially done for this class oriented architecture. But from class oriented architecture, what happened is, if you have class oriented architecture, the huge issue stays is, what is the problem with class oriented architecture? Problem is there is wastage. There is a lot of wastage, that if you give 192.162 to some person, some organization, that means that organization can, how many machines can this organizations, how many IPs does this organization have now? 2 to the power 16. And now how much is 2 to the power 16? How much is 2 to the power 16? 10 to the power, say into 0.3, 10 to the power 5. 10 to the power 5 means this is 1000, 10,000, 1 lakh machine. So 1 lakh machine. So 1 lakh machine. So any small, any like a big educational institute, like IIT KGP, a big educational institute like IIT KGP will have how many? we'll have 30,000 at most now, okay, 30,000 machines. So 70,000 IPs gets lost. So that's why this free structure, so that's why you see this free structure of IP where you have network which is an IP prefix, it's an IP prefix, and then you have the host. Okay, so this can vary. So if I say I want 16 machines, I want IP for 16 machines. So I want IP for 16 machines. So what should be the value? So you see here there is L and 32 minus L. So what will be the value of L then? How much is 32 minus L? Is 4. Okay. So L will be 28. So what will be my prefix? A 28 list prefix can be given to me. A 28 list prefix can be given to me. Okay. So a 28 list prefix can be given. Does that make sense? Okay. So 28 list prefix will be given. So just to see this, in more details, say you have the EE department which is taking the so now what I have written 128.208.0.0/18. So /18 means what? That out of 32 bits, 18 bits are prefix. Okay, so that means what? 128 point. So if this is there, then what is the range of machines I can? What is the range of machines? So let us say range of IPs EE can accommodate. So this is the question which I can ask. Okay, so now it is 128 is less. Okay, let me write 128.208.0.0. So here 2 to the power 8 is gone, 2 to the power 8 is gone. So now it is 18. So then if this is 0 0 0 0, okay, 0 1 2 3 4 5 6 7 8, huh? We have to write 8. Okay, 1 2 3 4 5 6 7 8. Okay, so first 2 is also in the prefix. Okay, first 2 is also in the prefix, and this is 1 2 3 4 5 6 7 8. Okay, so first 2 is also in the prefix. Now what would be the last address? So this part of the address cannot be actually shifted or changed because prefix is fixed for all IP addresses in E. So what would this be? 0 0. The last address would be 1 1 1 1 1 1 and all ones. Okay, so this is 255, and how much is this? 1 3 7 15 32 64. So 63. Okay, this is 63, 63, 127, 238. So 63.255. So 128, 208, 63.2. Okay. So what would be the next address? Exactly next address after this? What would be the exact next address after this? It is 128.208.01, all zeros. Sorry, all zeros. This is the exact next address from this. If you think carefully, exact next address is from this. And how, what is this? Tell me. 128.208.128.0. And if so now see the CS address, see the CS address carefully. So CS address is starting from here, and CS address is taking how many bits? It is taking 17 bits. So 17 bits means it is taking address up till here. Okay, it is starting from this, but it is taking address up till here. So what would be the last address of CS? If we think carefully, what would be the last address of CS? Can we think? What can be the last address of CS? So the last address of the CS will be 128.208, this 0 and all ones and all ones, and this all ones is how much? Yeah, we can just check this, but this would be very clear. So now see this, we have 194.24.0.0 to 194.24.7.255. Okay, 194.24.7.255. And when we do this, how many are there? There are 2048 things. And what is the prefix again? You see 194.24.0.0 and 21. Why 21? What is 2048? Tell me what is 2048? Is 2 to the power 11. So 2 to the power 11 addresses and 2 to the power 21 is the prefix. Okay. So 21 prefix and 11 address. Okay. So similarly you see this is 12, 22 and 2 to the power 10. Then this is 20 and 2 to the power 12. 20 and 2 to the power 12. So now what is happening? So if you want 2 to the power 12, so what is happening? Some company is telling I want 2 to the power 12 IPs. Then what is they are doing? They are giving the first 20 bits as same as prefix. They are giving first 20 bits and prefix and leaving the others for the company to use. Okay. Now what can happen in between? See, if I am entering 4026, although there is some IPs which are available, say 194.24.12.0 to 194.24 for 15.255, I am not giving it to Oxford. I am actually not giving it to Oxford. Why am I not giving it to Oxford? Because then I have to divide Oxford's address into two different prefixes. Then I have to divide Oxford's address into two different prefixes. Of course, I can do that, like I can have 194.24.12 22. This, as soon as I do this, 1024's addresses are gone. Then I can have 194.24.16.0 and 21. Okay. Then what will happen? 2048 will be gone. Still I need 1024 addresses. Then what will I do? It will be like 194.24.16 and this will be yeah, I think this will be 12, 16, I think it will be 32, 0 and 22. Then you will get, so this we have to check, but then you have to have 122, 121 and another 22. This part follow, that you have to have 122, 121 and another 22, which is difficult. Okay. Otherwise, so you are keeping this available whenever a new university comes in. Whenever a new university comes in England, they will assign this 1024 addresses to them. Fine. Okay. So this is about the IP addressing scheme, and then how do router matches? The router matches the longest subsequences. Okay. So longest prefix, sorry, so longest prefix. So router sees with which root the prefix match most. Okay. It assigns to that. So say this, that you have 192.16 point say 1011 something. So you have 192.16.0.017 and you have 192.16.0.016. Okay. So this is what it's a bit concocted, but I am just telling that you can have one which has 17 bits and one which can have 16 bits. Okay. So then if a packet is coming with 192.16.0.1, say something like this, it will match to the longest subsequence. It will match to the longest subsequence. Fine. So this is about IP addressing. So traceroute is just a command, and class oriented addressing is actually not used. Classless addresses are used. Okay, so class oriented address is just a, it is just a academic concept. The classless address is what is used. Okay, so we had this issue. We had this issue of that all the address space is not enough. We had this issue, number one, and number two, if you see in your college etc., all are local IP, but they go out. Okay, so but they go out and then get things back. How? Because outside people don't understand, outside people don't understand the local IP, or they don't recognize the local IP. Then how does it work? So here there is a concept of NAT box. So what is a NAT box? A NAT box is network address translation. So what is happening? You have 10.7.6.7 and it will convert it into 192. One 192.16.7.6. Okay. So the NAT address is 10.7.6.7 and it is getting translated to 7. So this NAT translator does. So this is fine, but then the question would be that many others will also get the same address. Many others like another 7.6.8 that will also get the same address. Okay, that would also get the same address. Then how, when a packet is coming back, 'When 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 with 192.6.7.6. It can be for this and it can be for this. So this network address translation, or see, if this was done as if this could have been made a external IP instead of an internal IP, this could have been made an external IP. Okay. So this is not, so this would not solve the problem. So now what happens is, see, now they take idea from transport layer. Okay. So in transport layer, what is there? There is a IP address and there is a port. Okay. So there is a IP address and there is a port. So now this port number is used. So what is happening? If I have a IP and port, IP plus port is unique. Okay. So IP plus port is unique. So now what happens? See, this is a NAT box. We say this is a NAT box or NAT table. Fine. So now you have a IP plus port. So this port, say this is 10.7.6.8, 5,000. So port number is 5,000. And now, so here when you are transferring, you can do it 192.7.192.16.7.6 and port number 5,000. Okay, port number 5,000. Although this port number doesn't stay in the IP header, it stays in the TCP header or UDP header, whatever you say, the upper level header, but still you can do this. What is the difficulty of doing this? What is the problem of doing this? That what is 5,000? 5,000 is source port. Okay. What is the problem of this? So you can have another 192.6.8 and that is also using port number 5,000. So that will also have the same address, and again while coming back we will have the same. So what is happening? So now let us try to understand things carefully. One is simply translating the IP address to IP address. Done. But then there is a many is to one mapping. Next is what? Next is, no, you keep the IP, you translate the IP address, but also give the port number as an additional identification. And this would be a little bit better. I would say that not many ports will have 5,000 similar, but still there can be 5,000 and there will be clashes. So then what do we do? What we do is we simply take this 1, 7, 6, 8 and 5,000 and do a hash function and get an entry in this table. So this table is this table is say from 0 to say 3644. So it's like 36,000 and you get 3417. From this hash function you get 3417. Okay. So now instead of 5,000, what will you put? 192.776.7.63417. Now the next thing which also has 5,000, it will hash and it will get somewhere here maybe 2416. Okay. And if it is 2416, then it will have 192.767.12416. Okay. So now they are differing in port and everybody is getting a unique port. Okay. And so this is the source port. So what happens is the source port So what is happening with this source port 192.76.7.1 source port? You are going to some service, okay, some service. So this is the destination IP, this is a source IP and source port. Source port is 3417 and there is some destination IP 201.6.7.6. Okay, there is some destination IP. Okay, and after coming back, it comes back with. So this server sends back packet now with this as destination. Sends back packet with this as destination, and now with as destination it comes to the NAT box. So in the NAT box, as soon as it says 3414, it goes to the 3414 entry and then says, oh, this should be replaced. So 192.7.67.1 is replaced with 10.7.6.8 and 3417 is replaced with 5000, and then inside the network. So what is happening? See that you are having multiple machines, they are all using the same IP. Only thing what they are doing is they are having a different port number. Okay. So what is happening? Virtually, what is happening? That we are getting many more connections than that can be achieved through a single IP. So a single IP is providing many more connections. Fine. So this is how NAT works. So there are some pitfalls of NAT. Like one very big pitfall is that, so it's a what layer protocol is this? What layer protocol is this? So is this a IP layer protocol or a TCP layer protocol? So it is a IP layer protocol. Surely it is affecting the IP, but it is using TCP's. It is using TCP's information. So this is again a cross layer protocol that way. It's a cross layer protocol that way. But see, one important premise on which it is working is that the upper layer will have port number. What happens if the upper layer doesn't have a port number? Then this will not work. And so what is happening? Because of this, see, the entire thing of the entire concept of layering is that one layer needs to be completely independent. One layer needs to be completely independent of the next layer. Unfortunately, in NAT, this is violated. Okay. So even if you change something in TCP layer, the IP layer will break down, which is not a very good thing. Okay, IP layer will break down. Okay, this is number one disadvantage, and this is the main disadvantage. Okay, so this is, you see, we have written that NAT violates the most fundamental rule of network protocol layering. So, so the point is, processes on the internet are not required to use TCP or UDP. That was the idea, basic idea, that processes on the internet, they can use any protocol. But now you are completely tied that you have to use protocols which use ports, and that is TCP or UDP. And since all the codes are written, port are from port is from say bit number 7 to bit number 10. So you have to keep port at bit number 7 to bit number 10 to have any NAT protocol working. Okay. And so what is happening, and again philosophically, IP was a connectionless protocol, and now IP is becoming a connection oriented protocol due to NATing. Okay. And then there are other problems. One is because of NATing, you cannot initiate, unless you initiate, nobody can contact you. Okay. So this is another problem, that any connection has to be initiated, otherwise you cannot get it. Another important problem is, if some application like FTP which inserts IP address inside their body, and that IP address is not in the header but is in the inside the body of FTP protocol, and that IP address is taken to do connection, okay, immediately it will not work. So this is all about NAT. So I guess we are at the pretty end of our routing protocols and IP routing protocol, so yeah, I will talk a bit about peer-to-peer protocol, which is also a very important protocol, and talk about CORD. Okay, CORD is the most popular peer-to-peer protocol. Okay, and CORD uses a concept of distributed hash table. Okay, DHT, distributed hash table, and we'll talk about distributed hash table. Okay, so yeah, as I told you, that trace route is nothing. Trace route is a command. Okay, so you give a command trace route, and that will trace the routes and show you which are the routes. Okay, and route is a route. Okay, so you use the command trace route to find the route. Okay, any further question on this? Otherwise, I will go to the CORD protocol. Okay, so the CORD protocol, quickly will tell, is, see, in peer-to-peer networks, what is happening? There is no server and there is no client. Okay, everybody is server and everybody is client. Okay, in peer-to-peer networks, no server, no client. So if there was a server, then there can be an hierarchical sort of design, that from server this machine 1 has gone, and machine 2 has gone, then machine 3, then machine 4. Okay, so some sort of hierarchical design could be there, in which way you will route. But here no hierarchy is allowed. No hierarchy is allowed. Then how? Then how to handle? This is the question. See, here there is no central control for routing, and there is no central data repository even. That if, so there is a concept called monitor in cloud. Okay, so where you can go and see other data. All those concepts are also not there. So two basic questions: how to make data of each node available, and how to find required information. So what is happening? First, how to arrange machines. Arrange machines so that no central control is needed. This is important. Okay, how to arrange machines so that no central control is needed. Okay, so now we talk about a DHT, or distributed hash protocol, and the protocol is called CORD. Okay, so see, CORD has, so the basics is that you have a IP address, and you hash that IP address and you get a ID. Okay. So, and what hash function you are using? You are using some SHA1 etc. sort of hash function. Okay. You have a IP address and you are using some sort of hash function which is SHA1. Okay. So, what happens? So, and it's a 160-bit ID you get. Okay. So, this is how technically every IP produces an ID. Okay. So, now you see the machines are arranged, the machines are arranged, you can see the machines are arranged in form of a circle. Okay. So, machines in form of circle. Okay, how they are arranged? So, let us say 1. So, 1 means the ID. Okay, it can have some IP, but its ID is 1. So, there is one machine. So, see the circle is say 0 to 231. Okay, the circle is 0 to 31, while inside that circle there are how many machines? 1, 2, 3, 4, 5, 6, 7. So, if I have IDs which is spanning from 2 to the power k, and you will have m machine 2 to the power k minus 1, okay, and you will have machines m is less than 2 to the power k minus 1. Okay. So, this is a condition, m is less than 2 to the power k minus 1. Okay. So, now you have some, we will talk about how you put machines, but say somehow you have magically put machines 1, 4, 7, 12, 15, 20, 27. 1, 4, 7, 12, 15, 20, 27. Okay. You have magically put machines 1, 4, 12, 15, 26 and 27. Okay. So, now if you have put machines, each machine has a finger table. Finger table means routing table. And how this routing table is coming? See, for 1, follow the routing table for 1. Okay. 1 is 1 plus 2 to the power 0. 1 plus 2 to the power 0 is 2. So, 2, if I have 2, then what is the next machine? Next, there is no machine at 2, there is no machine at 3, there is only a machine at 4. So, 4. Okay. Now, 1 plus 2 to the power 1. 1 plus 2 to the power 1 is 3. So, what is the next machine at 3? 4. Okay. Now, 1 plus 2 to the power 2, that is 5. And what is the next machine possible at 5? That is 7. Now, it is 1 plus 2 to the power 3. 1 plus 2 to the power 3 is 9. What is the next machine at 9? Is 12. And now, 1 plus 2 to the power 4, that is 17. What is the next machine possible after 17? 20. Okay. And since this is till 0 to 2 to the power 5, you go up till there. Okay. Because the next one is 1 plus 2 to the power 5, that is 1. Okay, you understand. Okay, 2 to the power 5 mod 5, that is 1. Okay. Very good. So, now you have filled up the finger table. Okay. So, once you have the finger table, how to traverse? This is the next question which you may ask, that once you have the finger table, how to traverse? Okay. So, now here you see, first let us assume that all machines are put. Now, say I am trying to put a document, or I am trying to index a document. So this concept is important to understand. I want to index a document. What does indexing a document means? Means I want, because this is a peer-to-peer network, I want to search a document. So in order to do the search, I have to index a document. Okay. So how do I do the document, index the document? I do a hash of this document. Let's say this document name. Okay. And I get a ID. Okay. And now I will try to put this ID in one of the machines. See, this ID is residing in machine 1. Say machine 1. This ID or this document is residing in machine 1. But if I put the index in machine 1, how will I search? I don't know how to search. So now see, during search time what will happen? Somebody X comes with document name, the same document name. Okay. During search, some X will come with the same document name, and the system does a hashing and gets a ID, and then the system search for this ID. Okay, the system search for this ID. So then what is happening? Search for this ID, and it sees that this ID is residing in, say, some machine 1, and in machine 1 there is a small table where it says that this ID is document name and it actually is in machine 1. Okay. So there are two things. Again, it's a little bit complicated, that document physically resides in machine 1 but is indexed in machine 5. Okay. So try to understand this, that document is physically residing in machine 1. It is, so say the document is in, this is a document which physically resides in machine 1, but it is indexed in machine 15. It is indexed in machine 15. Okay. So then what happens? Then what you do? First find the index and then find the physical machine. Okay. So now how do I find? First of all, how do I index? If you understand how do we index, then immediately you will understand how we find. Okay. So let us see how we index. So what happens? Say I have done this. So now I get, so this is the finger table, or let us go back a bit and see, this is the finger table. Okay, and I have a document, with, say, ID. Ultimately after hashing with ID, it has come as 14. Okay, with ID as 14. So if it is an ID at 14, then it should reside in the, so this ID at 14 and it is from machine, say 27, that is fine, but it should reside at the next available machine. Okay. So what is the next available machine here? If you go here, go back here, so it is 14, IP is 14, so the next available is 15. So it should reside at 15. Okay. So now what is, it should reside at 14, should reside at 15. So what is a naive way of thinking? that you go from 1 to 15. See, after 14 you check whether there is a machine at 15. But that how will we do? We don't know, because so what we need is how are machines binded together. Machines in a ring binded together. If you think, then there is the finger table or routing table. So say I have this routing table from where, say I have a simple routing table where I say one's successor is 4 and predecessor is 27. One successor is 4 and predecessor is 7. So now with 14 I know 1, so I go to 1 and say successor is 4, so I go to 4. 4 has also this routing table whose successor is 7. Okay, 7 is greater than 14 or less than 14. 7 is less than 14. So again I go to 7 successor. 7 successor is 12. 7 successor is 12. 12 is less than 14 or greater than 14. 12 is still less than 14. So I go to 15 and find 15 is greater than 14. So I put 14 as index here. Done. And when I am searching for 14, I go to 1, then go to 4, then go to 7, then go to 12, and then come to 15, and I get 14 address. This is simple. This is how it is worked. But what is the difficulty? This is a linear search, that you have to go from machine 1 to machine 4 to machine 7 to machine 12 to machine 15, and this way you have to go. So this is a simple linear search can be initiated. Okay, which is inefficient. Okay, a simple linear search can be initiated, but which is actually inefficient. So then what should we do? If it is inefficient, then what should we do? Then let us again go back to this route. Okay. So now see, first of all 14 here, see this 14. So or let us go back here and just take up it. So see, routing table, see this for 14. Let us talk about 14. So I know 14 is between 9 and 17. 14 is between 9 and 17. So then I just go to that point which is just below 14. So 9. 9 is just below 14. And what is 9 successor? Is 12. So I go to 12. Okay. And I go to 12. And what is 12's immediate successor? 12's immediate successor is 15. So immediately I know 14 will be decided. You can take something else, take 16. Okay, take 16. So 16, so you go to, again you have to go to 9. So you come to 12. So 12's immediate successor, 12's immediate successor is 15. So 15 it is not, so 16 is still more than 15. So 15 it will not work. Then it goes to say 12. Okay, let us think carefully. Okay, so 12. Okay, let us write just to understand. 12 plus 2 to the power 0 is 13. 12 plus 2 to the power 1 is 14. 12 plus 2 to the power 2 is 16. 12 plus 2 to the power, okay, 12 plus 2 to the power 4 is 12, this is 20 and this is 12 plus 2 to the power 28. Okay, fine. So, and what is 13? 13 is 15, 14 is 15, 16 is 20, 20 is 20 and 28 is 1. Okay, this is the finger table of 12. So, now come to 12. So, 12 which is just less than 16 is 15. So, now you go to finger table of 15. So, construct the finger table of 15. 15 plus 2 to the power 0 is 16. So, 16 is 20. Okay. Then 17 is 20. 15 plus 4 is 19. 19 is still 20. 15 plus 8 is 23, that is 27, and 15 plus 16 is 31 and that is 1. So, now 15 successor is greater than 16. So, you know 15 successor is greater than 16. So, then 16 would be in 20. So, how many hops you are taking? From 1 you are going to 12, from 12 you are going to 15 and from 15 you are directly going to 20. So, you are taking 4 hops. So, which may look a little bit more here, but actually at every hop if you see for the first hop you were at the 4th line, for the next hop you were at the 2nd line and for the last hop you were at the 1st line. So, what is happening if there are say 5 lines, you at every hop you will actually improve. You will be first at the 5th, then at the 4th, then at the 3rd, but you can improve even faster. You may be first at the 5th, then at the 1st and then at the 2nd, then at 0th. Okay. So, what is happening? What is the maximum thing which can happen is the number of lines in the finger table. And how many number of lines are there in the finger table? It is basically log of 2 to the power. So, if you have a k-bit addressing scheme, the time taken is k. So, then this is a logarithmic algorithm. So, this is a fantastic algorithm that you have a distributed thing and you have a distributed logarithm. So, I guess yeah, we can talk about then how do we put machines. The machines we also put at same thing. See, machine, say I have a machine now of 23. So, 20 it will come here and machines will have some other things as it comes here at 23, but it will understand what is its successor and what is its predecessor. And once it understands the successors and predecessors, it can accordingly also copy the routing table of the successor and predecessor and create its own route. And it can also happen that a machine may leave. When a machine leaves, it's what does if 24 is inside, say if 20 leaves, what will happen? 27's predecessor will become 15, but successor will not change. So, accordingly this change is made and the routing tables are updated. And what happens is 20 has many indexed material, those indexed material will go to 20. Okay. So, this is all about routing. I think in these 3 classes I have tried to cover various aspects of routing, starting from simple algorithm to IP and to peer-to-peer networks. Yeah, I guess we have maybe a couple of minutes or sometimes. So, can we just give them the question paper? Is the question paper uploaded? So, please do the question papers. There are interesting questions there. Please do those question papers, and any questions you have further, Any questions you have further, you can actually mail me, and surely I'll be happy to answer your emails. Anyway, let question paper be there. We need not. Can they see the question paper, or can they download the question paper? They can download this. Yeah, that is great. So the question paper is there, and the PPT also, I guess people have downloaded. So there are multiple choice questions, mostly multiple choice questions, which will actually give you an idea that how things are working. Okay. Try to do the question. So we have it organized from session to session, and then our proctored questions. Okay. So I guess we have a detailed things which you may use and also may use while teaching your students. Anyway, please feel free to contact me. Any emails will be answered. Okay. There is one question I see. I guess I have answered this question. Two machines are neighbor in IP means because I told you that within two IP machines there can be a lot of L2 routers. So that means two machines may not be physically wired, means connected through wire, because L2 routers don't have IP. And why do L2 routers don't have IP? Then they have to maintain an IP table, and that is very costly. That's why you will see that from your machine you go to the, say you go in your colleges also, you will see that there is the Wi-Fi router, okay, which is Wi-Fi access point, and from that Wi-Fi access point it goes to a box. All these things doesn't have a IP address, but they are physically connected to your machines. Okay, they are physically connected to your machines, right? So which is the best? So one thing is you can use mininet. So mininet is something which you should explore, which is a good thing for teaching students. Oh, scheduling, what does scheduling work means? Scheduling is a OS concept. It's not a network concept. So this I told that if you are connected to internet, ultimately you need an external IP, but most of the time you will not have external IP, and that is managed through the NAT protocol. Okay, that is managed through the NAT protocol which I taught. Okay. What is the best factor? Do mininet. Which is the best factor? The routing protocol. Let's use mininet. Okay. What is the uh, uh, what is the purpose of root invalidation routers? See, timers are there because packets may get stale, and you may have the same. See, if you we talked about the link state protocol, where you will see that the the route is constantly changing, and that change has to be actually incorporated, and that's why you have this router which tells that after some time this route is invalid. Okay. I guess it is fine. So let us thank you for hearing, and thank you for attending the class.